Hi, and welcome to Dr. V's Chemistry Webcast. Today we're talking about Coulomb's law. Here's what I'd like to accomplish in this webcast. I want to introduce Coulomb's law. You need to know what it is. We're going to really focus on the qualitative relationships. We're not going to do any mathematical calculations with Coulomb's law. That's possible, but it's not part of what we need in this course. And I also want to talk about why chemistry students need to know this. So it starts with the idea that you learned long ago that charges interact. You know that like charges repel. If you have a positively charged ion and another positively charged species comes near it, they're going to move away from each other. We see the same kind of pattern with two negatively charged species. They move away from each other. This isn't news, I hope. And we also know that opposite charges attract, right? That they're going to move closer to each other. All right, so what we want to be able to do with Coulomb's law is quantify this. And Coulomb actually did this through a very long process of investigations. We're going to jump right to the nitty-gritty. What does it all mean? So what we realized, or what Coulomb realized from his experiments, was that the attractive force, and we're going to focus on the attractive forces, is proportional to two things. It's proportional to the charges and the distance between them. Right, so Q1 and Q2 would be the magnitudes of the charges. If this is an attractive force, they would have opposite charges. And then the distance between the particles, really from the center of each one to the center of the other, is not an edge-to-edge kind of phenomenon. So these are the two factors that affect the strength of the Coulombic attraction. And we're going to leave it as a proportionality because we're not doing calculations here. But if you knew the proportionality constant, you could, of course, do the calculations. But the proportionality constant depends on the nature of the interacting medium, and that depends on, what particles are interacting. And so we really want to focus on what this means and not so much the numbers. So let's talk about charge magnitude. All right, we see that Q1 times Q2 is in the numerator of this expression. All right, so if we have a positively charged species interacting with a negatively charged species at some distance, right, there's an attractive force between them, and then let's say we calculated it, we actually have a numerical value. If the charge of, say, the positive ion doubles, what we see is the strength of the attractive force also doubles. So that's really what we need to pull out of this. All right, as the charge magnitude increases, the strength of the Coulombic attraction also increases. You need to know that. And now let's talk about the interparticle distance. All right, let's say we have, again, our two particles at some certain distance d, and they had a certain attractive force between them that we have a number for. And if that distance between them doubles, what happens to the attractive force? It goes down by a factor of 4. So what's important here to note is that as the distance between the particles increases, the strength of the Coulombic attraction decreases. Now, it is 1 over d squared. But what's really important, big picture here, is that it's inversely related. All right, so as the distance between them goes up, the strength of the attraction goes down. That's really what you need to remember about that. All right, I do know that charges have a more dramatic effect on the strength of the attractive force than the distance. So if you first look at charge and then you look at distance when you're dealing with Coulomb's law. So let's do some practice problems. Typical questions you might be asked might be which species in the pair will have the stronger Coulombic attractions. So if we're looking at iron 2 plus interacting with chloride versus iron 3 plus interacting with chloride, we would expect the iron 3 plus chloride interaction to have a stronger Coulombic attraction because iron 3 plus has a larger charge magnitude than iron 2 plus. Okay, what if we're comparing the interaction between sodium ion and bromide ion, between potassium ion and bromide ion? Well, for this, all right, we notice that both of them have the same charges. It's +1, -1 versus +1, -1. So it must come down to sizes of the ions and the internuclear distance, or the interparticle distance. We would expect the sodium and bromide pair to have a stronger Coulombic attraction than potassium ion with bromide, because sodium ion has a smaller radius than potassium. It does help to know your periodic trends to answer these questions. If you don't know them, I've got a webcast for you. What if we're looking at the attraction between magnesium ion and oxide ion, or lithium ion and oxide ion? Well, remember, we always look at the charges first. The higher the charge, the stronger the Coulombic attraction. So we would expect the magnesium ion oxide attraction to have a stronger Coulombic attraction than lithium ion to oxide ion. All right? So it comes down to the charge. And if we look at the attraction between calcium ion and sulfide ion versus zinc ion and sulfide ion, well, again, both pairs have the same charges, +2, -2. So it must come down to internuclear distance, which would here come down to ionic radius trends. All right. The zinc ion has a smaller radius than the calcium ion, so the calcium ion to sulfide attraction would be weaker. The zinc ion to sulfide attraction would be stronger. So these are the kinds of questions you might get asked. There are a lot of things we can ask about in terms of Coulombic attractions. We do use it a lot in chemistry. It shows up in many different places. So explaining why periodic trends occur comes down to Coulomb's law. So your atomic radius trends, your ionization energy trends, you need to be able to correlate these patterns into those trends for an explanation. Talking about photoelectron spectra, if you're taking AP chemistry and your teacher's talking about this, Coulomb's law can help explain what we see with those spectra as well. We also see that when we compare the strengths of intermolecular attractions, it comes down to Coulomb's law. Charges, distance between particles. All right. We can also use this to explain boiling and melting point trends for ionic compounds. Lattice energy arguments, another topic that comes up a lot in AP chemistry. So you do need to specify what kinds of interacting particles are involved. All right. So it can be atoms, it can be ions, it can be an ion to molecule attraction, it can be two polar species interacting, lots of options there. And so you do need to know what's interacting there. And it becomes a very important part, especially for your response questions. Can you use Coulomb's law to explain these different phenomena? Before we go, I want to remind you to subscribe to my channel. Come back and keep learning chemistry.